So in the last session, we were talking about the properties or the process of design of footing, especially the isolated rectangular footing. So I'll just go through what we have done in the last session. So initially we had got the problem statement with some amount of live load and as well as the dead load. And then based on the live load and dead load combination and also based on the condition of the column that is given. If it is a rectangular column, we have to design a rectangular footing. If it is a square column, we have to design a square footing. That's the usual thumb rule that people will follow in the real-time scenarios. And there is no exactly rule that for square column, you should design only square footing. But most of the times, it is something that is followed. So, and the grade of materials were also given, that is M20 grade of concrete and Fe415 grade of steel. And then the safe bearing capacity of the soil is also given along with the allowable settlement, which is 25 mm. So 25 mm is the maximum settlement that any footing, not just the rectangular footing or not just the isolated footing, any type of footing, whatever that we take, maximum settlement that one can undergo is 25 mm. So based on that, initially we have first determined the length and width of the footing by finding out the area of or the total area required for the footing. And then we have assumed the self weight of the footing as 10% of the column load. And based on that, we have got the area of the footing. And then in order to determine the length and width of the footing, we have found a concept called, or we have talked about a concept called projection length, that is called as X. So what is this projection length? So in order to have the uniform pressure distribution, we should maintain a distance of X or a projection length of X along all the four sides of the column, such that the even pressure distribution or uniform pressure distribution will happen. And also, if the settlement by any chance happens, the settlement will also be uniform. So that's where we talked about the centrally positioned columns and eccentrically positioned columns. So based on the positioning of the column, that is the projection length, we have determined the value of X. And then based on this factor, we have determined the length of the footing and the width of the footing. And then we have determined the upward soil pressure. And finally, we have determined the depth of the footing based on a condition which is called as a moment-based condition. So usually the depth of the footings is governed by two different criteria. One is called as flexural criteria and the second one is shear criteria. So as of now, what we have done is we have done the calculation with respect to the moment-based calculation. So that's where we have taken we have calculated the moment along the length direction and moment along the width direction. And among these two, whichever is the highest one, that we have considered as the ultimate moment or the maximum moment, you can say. Based on the ultimate moment, we have determined the depth of the footing and also based on the grade of steel. Okay, so that's how we have come up with the values of length, width, and depth of the footings as of now. So the next thing that we are going to design is we are going to design the reinforcement, which is called as AST, area of steel. So before we talk about how to do the design of reinforcement or how to find out the values of AST, it is important to understand what is the position or where exactly the reinforcement has to be placed. That's the important criteria that we need to understand. Suppose if you take a simple a simple footing, okay, this is how a footing looks like, okay, a rectangular footing or something like that. So here, whenever we apply certain amount of load, okay, whenever a footing experience or the column experience certain amount of load, what will happen is, I was telling that this portion is called as the stiff area. Okay, this portion is called as the stiff area. So whatever the amount of load that you apply or that is coming onto the footing from the column, this portion will never get filled. Okay, whatever the stiff area that I am talking about, this stiff area will never get filled. Why? Because it will have the uniform pressure distribution. That means whatever the load that is coming from the top, it will have the reaction force also. Okay, it will have the reaction force also. So the action force and the reaction force will get balanced, and hence this particular portion will be very stiff. Okay, nobody can disturb that particular portion. So what are the disturbed portions now? The left side cantilever portion and the right side cantilever portions will be the disturbed portions. So by using this one, we can analyze the approximate bending moment diagram of the footing, including the column. So how does it happen? It happens in this way. So let me go in this way. Suppose if we have the column in this way, and when the load is applying on the column, or when the load is coming through the column, so the footing might have a chance to bend in this way. Okay, this is one side and this is the other side, and this is how it goes. This portion, that is the stiff portion, will not experience any kind of bending. Why it will not experience any kind of bending? It is because whatever the action forces that are there, the reaction forces will be an equal one. So the action force is equals to the reaction force, and hence this stiff portion will not go in any of the deformed shape. The only deformation that occurs is the left side cantilever portion and the right side cantilever portion. Why is that? It is because we have the upward soil pressure that is coming here. Okay, we have the upward soil pressure that is coming on the left and right side of the cantilever portion, but we don't have any of the load that is coming from the top of these left and right side of the cantilever portions. There won't be any amount of load. Yes, obviously soil will be available here, but the soil force or the soil load will be comparatively less than when we compare with the upward soil pressure. So here in the cantilever portions, the upward soil pressure will be a dominating one. Okay, those loads will be the upward soil pressure will be the dominating one. Since the upward soil pressure is a dominating one, there is a chance that the cantilever portions will tend to bend in this way, as I'm showing in this figure. Okay, so here, which is the compression zone in the cantilever portion, the top force or the top zone is the compression zone, and the bottom zone is the tension zone. Okay, the top zone is the compression zone because the footing is getting compressed on the top surface, and it is getting tensile forces, or it is experiencing tensile forces at the bottom. So it is a tension zone. So by blind rule of design of reinforced concrete structures, we know that wherever we have the tension zone, in that zone, we have to provide the reinforcement. That's our blind rule. Design of reinforced concrete structures, where the tensile forces, not just in footings, in any type of structural members, if there is a tension force or if there is a dominating tension force, in that zone, in the tension zone, we have to provide the reinforcement. That's our rule. So now, when we design a footing or when we design the reinforcement for a footing, it is mandatory to identify what is the reinforcement that we have to provide in the tension zone. Okay, what is a reinforcement that we have to provide in the tension zone? Now here, if you ask me, don't we provide the reinforcement in the compression zone? Yes, we do provide the reinforcement in the compression zone, but it will be an minimum reinforcement, AST minimum. So we have the formula for that, which is 0.12% of B into D. That I'll tell about that one in some time. But whatever the reinforcement that we are going to determine now, that reinforcement is something which is determined in the tension zone. Okay, that is determined in the tension zone. That's why whenever we write the reinforcement determination, we always write it as AST. That means A represents area, S represents steel, T represents the tension zone, area of steel in tension zone. So that's what we are going to find out now. I hope this pattern of bending moment is clear for you. Right. So now let us identify the area of the reinforcement condition, and then we'll undergo the determination of AST, the maximum AST, the minimum AST, all those things. So here, as we know that, okay, as we know that the wherever we have, wherever wherever we have tension zone, in that zone, in that zone, we have to provide the reinforcement. That's our logic. Right. So we have known, as of now, we know that where actually the tension zone occurs, where actually the compression zone occurs. At the bottom of the foundation slab, we'll get the tension zone. At the top of the foundation slab, we'll get the compression zone. Right. So here, when we are finding the reinforcement, we have to find the reinforcement along the length direction and also along the width direction. Okay, length along the length of the footing and also along the width of the footing. So let me write in this way, along the length of the footing. So first we'll find out along the length of the footing, and then we'll find out the reinforcement along width of the footing. Right. So what is meant by along the length of the footing? Suppose if I have to draw the length direction of the footing, suppose if you take this as the image, let me do one thing. I'll just draw it here and then I'll copy it. Yeah. So if you talk about the length direction of the reinforcement, suppose if you take this as the rectangular footing, right? So this is the foundation slab. So along the length of the footing is nothing but we are going to provide the reinforcement along the length direction. So this is the length direction. So this is one steel bar. So likewise, we are going to provide the number of steel bars. Okay, let us consider this as the first steel bar. And then we are going to provide the reinforcement along the length direction. So this is how we are going to provide the reinforcement along the length. So along width is nothing but in the vertical direction. So this is the length direction of providing the reinforcement. But here the spacing will be calculated along the width. So when you are providing the reinforcement along the length direction, the spacing is considered along the width direction. That's the thing that we have to remember. So when you are providing the reinforcement along the length direction, spacing is taken along the width direction. Okay, spacing is taken along the width direction. This is the spacing between the two steel bars or the two reinforcement parts. Right. So now what we have to do is we have the formula to determine the area of steel, be it along the length or width direction. So this is the formula. AST equals to 0.5 times of FCK upon Fy into 1 minus under root of 1 minus 4.6 mu divided by FCK into BD square into B into D. This is the formula. So here FCK is nothing but the grade of steel, grade of concrete. Fy is nothing but grade of steel. Mu is the ultimate moment that we have to consider because we have found out moment along length and moment along width direction. So among those two, whichever is the highest that we have to consider as mu, and then the width, B is the width and D is the effective depth, not the overall depth, but the effective depth, right? So here, let us find out the values of all these things. So I'll just write the values, that is FCK, the value of FCK is 20. Okay, the value of FCK is 20 newtons per mm square or 20 MPa we can say. And the value of Fy is 415 MPa, that is grade of steel. And then the let's say what else? Mu, the maximum moment. Mu is okay, Mu equals to, I think it is 520 something. Yeah, 520.05. Along the length direction, the moment value is 520.05 kilonewton meter. And then the width direction. So what is the width of the footing? The width of the footing is 2.25 meters, if I'm not wrong. Yeah. So the width of the footing is 2.25 meters. So B equals to BF equals to 2.25 meters. So I'll just make it as in mm, that is 2250 mm. And then the effective depth. The effective depth of the footing is something around 600 we have got. Let me just check that. Yeah, it is 592 mm. Okay, that's the effective depth of the footing, not the overall depth. Remember, it is the effective depth. So this is how we get the values of all these things. So once you substitute all these values in this one, you're going to get the area of steel, that is AST equals to, if you solve this one, you will be getting the value as 2534.35 mm square. So this is the area of steel along the length requirement or along the length of the footing. But remember here, when you are finding out the area of steel, the mu should not be taken as the maximum one. What you have to take, since we are calculating the reinforcement, that is AST value along the length of the footing, whatever the value of mu that is there along the length of the footing, here you can see. So mu along the length of the footing is a 520.05. You have to consider this one, not the maximum one. Okay, that's what it represents. That's the only thing that we have to remember here. So this is how the area of steel can be found out based on the condition of moment or ultimate moment along the length direction. Right. So this is basically the design requirement. Okay, this is what we have to provide. But in actual scenarios, we cannot provide exactly this much. So we have to round off this value. So how to round off this value? So in order to round off this value, we have to first calculate the minimum reinforcement, AST minimum we will call it as. Okay, the minimum reinforcement that is available. So what is the formula for minimum reinforcement? The minimum reinforcement is, the formula for minimum reinforcement is 0.12% B into D, that is overall depth. Okay, 0.12% B into D. So what is 0.12%? 0.12%, I'll just write as it is, into B. What is B? B is the width of the footing. What is width of the footing? Width of the footing is 2250 mm. Okay, 2250 into the overall depth. Overall depth we have considered as 650 mm. Okay, the overall depth we have considered as 650 mm. So let me write it as 650. So therefore, you are going to get the reinforcement or AHT minimum as 1755 mm square. This is the minimum reinforcement that we have to provide. What is the design requirement? Requirement is this much, but minimum you have to provide this much. At any case, you have to provide minimum to minimum of this size of or this area of the reinforcement. Now, as I was telling in the last session, the diameter of the steel bars, which we generally consider in the design of footings, is 16 mm diameter bars. So provide 16 mm diameter, provide 16 mm diameter of steel bars with a cover of or with a clear cover of 50 mm. Usually for footings, we provide it as 50 mm as the clear cover. So from this, we can calculate the spacing required. So spacing required equals to so how will we find out the spacing? So pi by 4 into d square. What is d? D is the diameter of bar, which is 16 square. Okay, pi by 4 into 16 square will give you 201.06. Okay, 201.06 upon the area of the steel, which is the design requirement. What is design requirement? 2534.35. Okay, 2534.35. So how does this 201.6 has come? So I'll just make it in this way. So pi by 4, I'll just make it as pi. So pi by 4 into d square, where d is the diameter of the bar. Okay, d is the diameter of bar. Let me write that also. D is diameter of the bar, that is 16 mm. So from this, we are going to get the value of 201.06 upon the design reinforcement requirement, which is 2534.35. Once you solve this one, you're going to get the spacing value. So the spacing value is will come as 178.5 mm. So we don't provide exactly the same amount of spacing. Usually, whatever the spacing value that we are going to get, that spacing value, we will reduce it. Instead of increasing the spacing value, we will consider the reduction in the spacing value. Let's say I'll provide the spacing as 150 mm. Okay, 150 mm center to center spacing along width of foundation. Okay, along width of foundation or footing, you can say anything. So why I'm reducing it to 150 mm? Why not I don't try and round it off to 180 mm, or why not I go for 170 mm or 160 mm? Why I'm directly reducing it to 150 mm? There is no specific reason for that. The one common reason that we talk in the textbooks is the more the spacing, the less will be the number of bars. Okay, that's a simple thing. So the more spacing you provide in the reinforcement, the less will be the number of parts. When the less will be the number of parts, the the spacing between the reinforcement will be very high. When the spacing between the reinforcement is very high, what actually happens is the distribution of the the distribution of the loads or the distribution of the moments will not happen properly. since the distribution of moments will not happen properly, what we do is we will reduce the spacing. When you reduce the distance between two bars, then you have to provide more number of reinforcement bars. So when you provide more number of reinforcement bars, then there will be an equal amount of pressure distribution. That is, tension zone reinforcement distribution will happen in a proper way. So that's the only thing that textbooks will say. Whatever textbooks you refer with respect to the design of reinforced concrete structures, that's one thing that often authors will say. That's the only reason why we are reducing the spacing of the footing than the value whatever we are getting. Okay, it's always important that one. So don't round it off to the nearest next value. You round it off to somewhere along plus or minus 20 or 25 is approximately fine. Okay, whatever the spacing value that you are getting, just reduce that value by 20 or 25 mm. Then you will be getting that approximation value. Right. So this is the spacing that we have to provide. So now let us find out the AST provided. Okay, AST provided equals to, so how will we get the AST provided? The 201.06, that is pi by 4 into d square. D is the diameter of bar, that is 16. 201.06 divided by spacing. What is spacing value? 150 mm is the spacing into, okay, into the value of the reinforcement, which is 2250. Okay, which is 2250. So let me write that value. That is not spacing, it is the width of the footing, 2250. So this is how we are going to find out the reinforcement values. Let me just keep it in this way. Yeah, so AST provided equals to 201.06, which is the diameter, the area of one steel bar of diameter 16 mm and divided by spacing, that is 150 mm, into the width. Okay, into the width of the footing. The width of the footing is 2250. That is what we have taken. So that equals to, we are going to get the AST provided value. So that will be 3015.9 mm square. 3015.9 mm square. So this is the amount of reinforcement that we have to provide. So what is the requirement? Requirement is 2534. How much we are providing? We are providing 3015.9. You can say 3016 mm square is the reinforcement. So it will be safe only. There won't be any problem. But by any chance, if you reduce or if you increase the spacing value, then obviously this value will get decreased. Okay, this value will get decreased. So the more the spacing, the less will be the number of bars that are required. So therefore, when there is less number of bars, obviously the total area of the steel will also get reduced. Right. So now what we have to find out is we have to find out the percentage of steel. So which we generally call it as a PT, percentage of steel. So PT equals to, the formula is AST divided by B into D. That is overall depth. So what is AST value? AST value is 3015.9 divided by width of the footing, that is 2250, into the overall depth. The overall depth of the footing is 650 mm. So into 100, you will get it in terms of percentage. So that equals to 0.206 percentage. Okay, 0.206% of reinforcement is required. So that's how we are going to find out, right? So this is the reinforcement along the length direction. Okay, this is the reinforcement along the length direction. Similarly, we have to find out the reinforcement along the width direction as well. Okay, we have to find out the reinforcement along the width direction as well. So let me just do the changes here. So along the width of the footing, the formula remains same, that doesn't change, but mu value will get changed. The mu along the width of the footing is, let me just check that, it is 561.05. So that's where the value gets changed here, 561.05 kilonewton meter. And then the width of the footing, okay, the width of the footing along the width direction, that is B value is, it is actually the length, it will become length. So the length of the footing is 2500, that is 2.5 meters. So 2500 will be the length of the footing, and the depth remains same, which is 592 mm. The overall depth is 650 mm. So from this, if you solve this one, you're going to get the area of steel along the width direction, which is 2730. Okay, 2730.76 mm square. This is the design requirement, and AST minimum. So here 0.12% of BD, where B value is 2500. That is 2.5 meters. So when you solve this one, you're going to get the value of AST minimum as 1950. Okay, 1950 mm square. And then we are going to provide the same number of same diameter of the steel bars, that is 16 mm, with a cover of 50 mm. Cover remains same both on top as well as at the bottom. So the spacing required equals to 201.06 divided by this value, which is, just give me a second. I just have to calculate. So AST is, yeah, I have made it, which is 2730.76. Okay, 2730.76. That is a design requirement. That value will become, it will be somewhere around 184.07. Let me just calculate that. 184.07 mm. So we are going to round it off to nearest 20 or 25 mm. So let me take the spacing as same. I'll just consider it as 150 mm center to center spacing also along the length width direction as well. And then AST provided equals to 201.06 upon 150 into the design requirement, which is, sorry, it is the length, that is 2500. So therefore, you're going to get the AST provided value as 3351 mm square. Will be exactly 3351 mm square. So let it be like that. Right. So from this, we are going to find out the percentage of steel that will become 3351 upon 2500 into 650. That it will give you the same value of percentage of reinforcement, which is 0.206 percentage. So that's how we are going to find out the reinforcement along the length direction and reinforcement along the width direction. That's the determination of reinforcement. Now, the next thing is the next and the last thing you can say, which is the shear criteria. As of now, we have calculated the flexure criteria. I was telling that it is the depth of the footing is influenced by two criteria. One is called as the shear criteria, and the second one is called as flexural criteria. Whatever the things that we have done so far, all those things are dependent on flexural criteria, that is moment criteria. Now we have to find out the with respect to the shear criteria. So let me call it as shear check. Let me call it a shear check. So here we are going to get two types of shears in footings. One is called as one-way shear and the other one is two-way shear. So let me write it as check for one-way shear. Okay, check for one-way shear. So usually in order to check for one-way shear, we need to understand one concept here, which is the critical section concept. You take any type of footing, the critical section for one-way shear is considered at a distance d from face of the column. Let me show you that image first. Yeah, so this is the image I was talking about. So the critical section is taken, or the critical section for one-way shear is always acting or will always act at a distance d from the faces of the columns. So this is one face of the column and this is another face of the column. So along all the four faces, the critical section will be at a distance d from face of the column. So if you consider this as the face of the column, so this small one is the column that we know. So if you consider this as the face of the column, from here at a distance d, we have to find out this d value. Okay, from here at a distance d, the critical section will act. This is the position, or this is the place where the section or where the foundation slab will get failed. That's why we are calling it as a critical section. This portion will never get failed. Okay, whatever the distance that is there before D, this entire portion will never get failed. Whatever the section that gets failed, initially the failure starts from this critical section only. Once this critical section gets failed, then the cracks will propagate towards the interior surface of the foundation slab, and then the column gets failed. That's how the failure criteria, or that's how the crack pattern will appear here. Right. So the critical section for one-way shear is considered at a distance d from face of the column. Let me write that. The critical section for one-way shear is considered at a distance d, at a distance d from the face of the column on all sides. In the figure, I have just represented with only two sides because it is same. So that's why I'm representing with only two sides, but it actually will be there on all the four sides. Right. So now let us find out the critical shear force. That is the capital V. Shear force is represented with capital V. So capital V. So here, shear force we have to calculate both along the length as well as along the width direction. So one-way shear, okay, one-way shear along length of the footing. One-way shear along length of the footing. Right. So let us find out the one-way shear along the length of the footing, which is defined as a capital V. Okay, V is with shear force. So capital V equals to upward soil pressure. Okay, upward soil pressure into the width of the footing. Okay, width of the footing into L minus A. The length of the footing minus A. Here it is into, yeah, L minus A divided by 2 minus D. Okay, L minus A divided by 2 minus D. This is the formula to find out the shear force along the length direction. So when you are finding out the shear force along the length direction, we are going to consider it as the width of the footing. Okay, we are going to consider the width of the footing, right? So let it be like this only. So now let us find out the shear force value. So capital V equals to upward soil pressure is something around 290. Let me just check that. Yeah, it is 293.33. So upward soil pressure equals to 293.33 into the width of the footing is 2.25 meters. Okay, 2.25 into the length of the footing. So what is the length of the footing? Length of the footing is 2.5 meters. Okay, that is length minus A. What is A? A is the length of the column, this line. Okay, A is the longer length of the column. So what is the length of the column? The length of the column is, that is the longer distance, is 450 mm. The shorter distance, that is B value, is 230 mm, and the longer distance, that is A value, is 450 mm. So therefore, A equals to 450 mm. So I'll just make it as in terms of meters, that will become 0.45 divided by 2 minus D. What is D? The effective depth, which is 592 mm. So I'll just make it in terms of meters, that is 0.592. So from this, we are going to get the shear force value, which will become 285.77 kilonewtons. So this is the amount of shear force that is coming along the length of the footing. But we should not always consider the shear force as this one. We have to consider the factored shear force. So the factored shear force is represented with the VU, that equals to 1.5 times of the shear force, that is 285.77. So that will give you 428.665 kilonewtons. So this is the amount of shear force that will be acting on the length direction. So this one we have to check with tau V, that is critical shear force. Okay, or critical shear stress, you can say. So I'll just make it as TV, or you can call it as tau V, anything is fine. So tau V equals to, we know the formula, which is VU divided by B into D. Okay, VU divided by B into D. What is VU? 428.665 into, I'll just convert in terms of newtons. So into 10 cube. Right. For VU divided by B into D. What is width of the footing? 2250 into the depth of the footing is 592 mm. So from this, we are going to get the value as 0.322 newtons per mm square. So this is the tau V value. Right. So now what we have to do is, in order to find out the shear at critical section, we should also know what is the available percent of steel at the critical section. Okay, to find the shear, okay, to find the shear at critical section, we should know available percent of steel at that section. So what is the available percentage of steel? That is PT value. PT along the length of the footing. Because why we are calculating along length? Because one-way shear is being calculated along the length of the footing. So in order to find out the shear at critical section, we should also know what is the percentage of steel at that section. That section is nothing but along the length of the footing. So let us see what is the value of PT along length of the footing. So this is along length of the footing, and the value of PT along length of the footing is 0.206. 0.206. So PT, let me write that PT along length of the footing equals to 0.206 percentage. Okay, 206 percentage. Now from this, we have to find out one value, that is the tau C value. Okay, tau C value. Let me just, so here the grade of concrete is M20. I'll just make it as M20. Now, if you refer IS 456, okay, as per IS 456 2000, as per IS 456 2000, clause 40.4, especially that is table 19, if I'm not wrong. Let me just check that. I'm just not sure about the table number, but let me write that. I think it is table 19 only. So if you refer this table 19, just give me a second. I'll just share you the IS code with the table. Just a second. I'm just stopping the screen sharing. Just give me a minute. I'll just check the code book and then I'll share the screen. Just a minute. Yeah, it is table 19 only. Let me share the screen. Right. I hope you are able to see the screen. Can somebody please confirm me that? Are you able to see the screen of table 19 that I'm displaying currently? Yeah, fine. So here, from this table 19 of IS 456 2000, if you see the design shear strength of the concrete, that is represented with tau C. You can see it here. So in order to find out the design shear strength, what we need is, we need the percentage of steel, so which is this one, right, the percentage of steel, and we also need the grade of concrete. In our case, the grade of concrete is M20. Okay, the grade of concrete is M20, and the value of PT. So what is the value of PT? It is 0.206. 0.206 percentage. That's the percentage of steel that we have currently. So here, if you see, it is starting from 0.15 and then 0.25. So 0.206 will be lying in between 0.15 and 0.25. Okay, so that means the grade of concrete is M20. So therefore, for 0.15, the value of tau C is 0.28. For 0.25, the value of tau C is 0.36 for M20 grade of concrete. If you have other grades of concrete, you have to approximately consider that different grades of concrete. Right. So here, in this case, for 0.15, the value is 0.28, and for 0.25, the value is 0.36. Since 0.206 is lying in between these two values, and considering this one, and then we have to do the interpolation, and we have to find out the tau C value, that is shear strength of concrete, for PT equals to 0.206 percentage. Let me write that. So let me go here. Let me delete this one. Yeah. So from table 19, if you see, so let me just make it in this way. Right. So here it is, I'll just make it as a PT and this one as tau C, that is shear strength in concrete. Let me keep it in this way. Right. So the PT value that we have is 0.150. I think that is the one. Let me just check that. Yeah. So 0.15, the tau C value is 0.28. So let me write that 0.15. For 0.15, the tau C value is 0.28. So in between that, we have our value that is 0.206. Okay, we have to find out this value. And then the other dimension is 0.25, the value is 0.36. Okay, for 0.25, the value is 0.36. So for this, if you do the interpolation, I hope you are aware of how to do the interpolation. So I'll not go into the details of that one. So we can get the value of tau C when PT equals to 0.206, the tau C value equals to 0.3248. Okay, that is in terms of megapascals, that is newtons per mm square. So this is how you are going to get the tau C value. But the condition here is always the tau V value must be less than tau C. Okay, tau V value must be less than tau C. So when the tau V value, what is tau V value? Tau V value is 0.322 and then tau C value is 0.324. So tau V is less than tau C only. So since tau V is less than tau C, what we can adopt from this one is provided depth. So therefore, provided depth is safe in one-way shear. So what is the provided depth? The overall depth that we have provided is 650 mm. So that is actually safe in shear criteria also, especially along one-way shear criteria along the length of the footing. We still have to satisfy the width of the footing also. Both conditions has to be satisfied. Only then we can say the adopted depth is safe. So provided depth is safe in one-way shear along length of the footing. Right. So now let us calculate the one-way shear along the width of the footing. Same calculations, nothing much change. So I'll just copy this entire one and I'll change the values accordingly. Right. So one-way shear along the width of footing. One-way shear along the width of the footing. So width of the footing is BF. So the formula remains same, which is V equals to upward soil pressure into the length of the footing. So here it's not width, it should be length. Length of the footing into, instead of L minus A, here we should get it as a B minus B. That is width consideration. B minus B by 2 minus D. Okay. So therefore, once you knew, when you solve this one, you're going to get the value as 306 kilonewtons. Okay, 306.52 kilonewtons. Okay, here upward soil pressure and length of the footing. So the value of capital B is 2.25 and the value of small b is 0.23. That is side of the column. Okay. So 230 is the smallest side and 450 is the longest side that we have seen, that is given in the question itself. So from this, we are going to get the value of shear force and then the ultimate shear force will become 1.5 times of 306.52. So that will become 459.79. 459.79 kilonewtons. So therefore, tau V equals to 459.79. Okay, 459.79 into 10 cube divided by the width of the footing. That is the length consideration, which is 2.5 meters. That is 2500 into 592, which is depth. So that will become 0.310. Okay, this is the tau V value. Similarly, we have to find out the PT value when it is 0.206 because the percentage of steel along the width consideration is also same, which is 0.206. Along length also it is same and also along the width it is same. So if it is different, you have to go with the different values. So I'm just going with the same value since we got the same value. So therefore, the tau c value will remain same, which is 0.3240. So 0.15, 0.206, 0.25. So therefore, when you solve this one, it will become tau v less than tau c. Okay. So when you see the tau v less than tau c, let me go here. Yeah, this one. So 0.3248. So tau v less than tau c will be there. So therefore, the provided depth will be safe along the one-way shear along the width of the footing. So let me write this as width of the footing. There won't be any change because the percentage of steel is not changing. So obviously nothing will get changed. If it is getting changed, I mean, if the PT value gets changed, obviously the other factors will also get changed. Right. So now this is all about the one-way shear calculation. Now let us do the calculation for two-way shear. Okay, let us do the calculation for two-way shear. So let me call it as 7.2. 7.2. So check for two-way shear. Check for two-way shear. Right. So here, in order to calculate the two-way shear force, again we have to consider the critical section. So usually in critical section, I mean in two-way shear, the critical section will be at a distance d by 2. Yeah. Any doubts?
Yeah, sir, what if tau v becomes greater than tau c? How do we
Then you
proceed
have to
with the
increase the
design?
depth. You have to increase the depth.
All right,
That's
okay.
what, if you remember, I think day before yesterday's session, we have discussed that only. So we are going to round off that value to a maximum one, so that if the tau v less than tau c, then it is fine. Whatever the depth that we have considered, it is safe. It is within the limits only.
Oh,
By any chance,
oh.
if tau v greater than tau c, then you have to increase the depth and you have to do the calculations again.
So we have to do it from the beginning, like
Not from the beginning, but from the
from the
shear
depth
force
part.
calculate. Yes, exactly. From the depth
Okay,
part, you have to
okay,
calculate up to the shear calculation.
okay,
So to avoid that confusion or to avoid that unnecessary calculation, I told that you take the value as a maximum one, so that if by any chance, if that becomes over requirement, then you can decrease it to a smaller extent. So then there won't be
okay,
any greater changes in the values.
okay, sir. Thank you.
Right, right. So the check for two-way shear. So two-way shear is also called as a punching shear force. Okay, we have talked about the types of failures of foundation: global shear, local shear, and punching shear. So for two-way shear, you can also call it as punching shear. So usually when we are calculating the two-way shear force, we have to consider the critical section. The critical section for two-way shear, okay, the critical section for two-way shear is considered at a distance d by 2 from the face of the column, on all sides. Let me show you that image so that it will be clear for you. Yeah, this is the image I was talking about. So two-way shear force is considered at a distance d by 2 from face of the column. So along the width of the column, so this is the d by 2 distance. Along length of the column, this is the shear calculation. So this is the critical section. Okay, this will be the critical section. So the other portions will not be the critical section. Right. So here, in order to determine the two-way shear force, the critical section is considered at a distance d by 2. Whereas for one-way shear, the critical section is considered at a distance d from the face of the column. Right. So here we need to understand this image first. So first let me explain you. Here you can see along the length, what I have written is 0.45 plus d. What is this 0.45? 0.45 is the length of the column, which is given in the question, 450 mm, plus d. What is this d? It is, so this side it is d by 2, and this side also it will be d by 2. So let me write that. So this side it is d by 2, and this side also it is d by 2. So d by 2 plus d by 2 is d. So therefore 0.45 plus d. Similarly, this side of the column, okay, this side of the column we know, which is 0.23. Okay, 0.23. So 0.23, that is the width of the column, that is 230 mm, plus d. So what is this d? Here it is not 0.4, it is 0.23. I have a correction here. It is 0.23. So 0.23 plus d by 2 plus d by 2. That is along the width. So d by 2 plus 0.23 plus d by 2. That is d by 2 plus d by 2 is d 0.23. So 0.23 plus d. So that's how these calculations has come. Okay, 0.45d and 0.23 plus d. Right. So from this, what we have to do is we have to calculate the same shear value, that is V value. So shear along the width direction, that is along the two-way shear calculation, capital V equals to the same formula, which is upward soil pressure, okay, upward soil pressure into the width of the footing. Let me call it as width of the footing, that is B into length of the footing minus 0.45. 0.45 plus D into 0.23 plus D. So this is how we can calculate the shear along the two-way shear force or two-way shear calculation, you can say. So it is very important to have these two things as the major ones. If you do any kind of mistakes, so I'll give you one problem where you can solve on your own. So when you are solving, you try to keep an eye on this consideration. So for all the problems, this value will not be seen. It depends on the dimensions of the columns. Okay, if the dimensions of the column get changed, obviously this 0.45 and 0.23 will also get changed. Okay, right. So here, what is D value? D is the effective depth. What is effective depth? 0.592. That is 592 mm. So I have just directly given this value here also. So once you solve this one, you are going to get the value of V. So upward soil pressure, we know width of the footing, that is 2.25 meters, length of the footing is 2.5 meters, and the value of D is 0.592, that is 592 mm. So once you solve this one, you are going to get the shear value as 1398.73 kilonewtons. So this is the shear force value. So now let us calculate the ultimate shear force, that equals to 1.5 times of 1398. 1398.73. So that equals to 2098.106 kilonewtons. So this is the ultimate shear force. Now, what we have to do is we have to consider the perimeter length of the shear area. So this is our shear area, right? So this is our shear area. So we have to calculate the perimeter length. So how to find out the perimeter length? So perimeter length of shear area. Okay, perimeter length of shear area, I'll just call it as B dash. Some representation I'm giving, so I'll just give it as B dash. So B dash equals to, so how will you calculate the perimeter length? So here you have 0.45 plus D along two sides, along this side and also along this side, and 0.23 plus D along this side and 0.23 plus D along this side. So therefore, the perimeter can be calculated as 0.45, okay, 0.45 plus D, that is 0.592 along length, okay, into 2, because we have two sides. So this is along one side. Okay, let me show it here. This is along one side and this is along another side. Now we have to make it as along this side and also along this side. Right. Let me do that. So 0.45 plus 0.592 into 2. Into 2 is because we are getting along two sides. So that's why I'm making it this way. Right. So this one plus along the length direction, along the width direction also, which will be 0.23 plus D. So what is D value? 0.592 into 2. So we have two sides. So 0.592. So that will become the perimeter length of shear area. So if you solve this one, we are going to get the value as 3.728 meters. Okay, 3.728 meters. That will become 3728 mm. This is the perimeter area. So why we are calculating this perimeter area? Because we have to calculate the nominal shear at critical section. So let me write that. So nominal shear at critical section. So I'll just call this one as tau V. Okay, nominal shear, I'll call it as tau V. So the formula is VU divided by VU by BD is for one-way shear, VU by B dash into D. So what is B dash? B dash is the perimeter length. So that's why we have calculated the perimeter length. So therefore, VU value we know, which is 2098.106. B dash value we know, which is 3728 mm. And D value we know, which is effective depth, that is 592 mm. So if you solve this one, you're going to get the value as 0.9507 mm. 0.9507 mm. So this one we have to check whether tau v is less than tau c or tau v is greater than tau c. So in order to do that, we have the calculation from IS 456 2000. So as per IS 456 2000, as per IS 456 2000, clause number 31.6.3 or 31.6.2. I'll just check that. The page number I remember, which is page 58. Let me check the page number 58, then I'll show you. Let me go to that page. Yeah, it is page number 68. That is 31.6.3. Yeah, permissible shear stress, tau C value. So let me write that one. So 31.6.3. Yeah, page number 58. What you have to do is shear at critical section. There will be one formula, shear at critical section. So how to calculate the shear at critical section is, there is one formula, that is tau c into Ks. Okay, tau c into Ks. Let me show you that one. You can see here. So when shear reinforcement is not provided, the calculated shear stress at critical section shall not exceed this part, this particular portion. When shear reinforcement is not provided, the calculated shear stress at critical section shall not exceed Ks into tau c. That's what tau c into Ks I have written. Okay, so from this tau c into Ks, what is Ks value? Ks value is given here. You can see here. So Ks equals to 0.5 plus beta c. So at any case, the Ks value should never be greater than 1. By any chance, if the Ks value becomes greater than 1, you have to consider as 1 only. Okay, you have to consider the value as 1 only. And the value of tau c, and the value of tau c is taken as 0.25 times of root FCK. That is in the limit state method. Whereas in working stress method, 0.16 root FCK. Whatever the structures that we design, the normal structures, we all design it in terms of limit state method only. Until or unless you are constructing a dam or a reservoir or mass concrete structures, in that cases only we'll go for working stress method. So currently we'll take the tau c value as 0.25 root FCK. Right, let me write that one. Right. The shear at critical section is tau c into Ks. So what is the formula for Ks? Ks equals to 0.5 plus beta c. I'll just make it as BC or beta c. I'll just make it as. So how to calculate this beta c value? The formula is the shorter side of the column, the shorter side of column divided by longer side of column. That's the formula to find out a beta c. So shorter side of the column is 230 mm and the longer side of the column is 450 mm. So the ratio will become 0.511. This is the ratio. So from this, the Ks value can be found out. That is Ks equal to 0.5 plus beta c. Beta c is 0.511. So obviously it will be greater than 1. So 0.5 plus 0. Let me just calculate. I'm not sure about the exact value. So 0.5 plus 0.511. So 0.511. It is 1.011. So it is greater than 1, 1.001. So even though it is greater than 1, okay, it is greater than 1, we have to consider, okay, therefore, consider Ks equals to 1 only. If it is less than 1, okay, if the Ks value is less than 1, you have to consider that value. Suppose let's say instead of 1.001, let's assume that we have got the value of Ks as 0.68. So when you are calculating, the value of Ks is also taken as 0.68 only. Okay, by any chance, if it is greater than 1, okay, if it is greater than 1, then we have to consider as a 1 only. Okay, that's one condition. Right. So therefore, consider the value of Ks as 1, and then we can calculate the tau c value, that is tau c equals to 0.25 into FCK. What is 0.25 into root FCK? So what is root FCK? Root FCK is a 20. Okay, 20 power 1 by 2. I'll just make it as that is a root value. Okay, 20 power 1 by 2. So from this, you're going to get the value of tau c. That will be 1.118 megapascals. So here we have to check whether tau v is less than tau c or tau v is greater than tau c. So what is tau v value? 0.95 and tau c value is 1.118. So tau v is less than tau c. So what does it mean when tau v is less than tau c? Therefore, the provided depth is safe in two-way shear also. So both in one-way shear and two-way shear, the depth is same. I mean, the depth is within the limiting condition. If in any case, either in one-way shear or in two-way shear, if the value of tau v is greater than tau c, even in one case also, you have to revise the depth. That's the condition. In both the cases, it should get satisfied, both in one-way shear as well as in two-way shear. Then only the shear criteria will get safe. If only flexural criteria is getting safe, it is not the requirement. Both in shear criteria as well as in the flexure criteria, the depth should remain safe. So this is the entire design process of the isolated rectangular footing. So once you arrive at this one, let me just write the final details or final design details of footing. So what are the final design details? That will be length of the footing that equals to 2500 mm, and the width of the footing is 2250 mm, and the depth of the footing is 650 mm. Okay, and then the reinforcement. Okay, reinforcement along length equals to. See, we are going to provide. You can just write the value whatever that we got here. I'm just writing it with 16 mm diameter of bar at a spacing of 150 mm center to center. The same value we have taken along the width direction also. Reinforcement along width equals to 16 mm diameter bar at a spacing of 150 mm. So this is how we can work with the design of rectangular footing or isolated rectangular footing. Right. So this one I have just made it as like too much detail because since this is the very first type of footing that we are designing manually, I just discussed about each and every step. So the same steps, more or less the same steps will be replicated in the remaining design details also. So I'll not be going into this depth when I'm discussing the other types of footing. Let's say in tomorrow's session, I'll talk about isolated square footing. The square and rectangular footing, they both almost are same. So there won't be much difference in that except the dimensions part. But when it comes to the sloped footing or trapezoidal footing, there we have to consider some other design calculations. So what I want to say is I'll not be going into this depth as we have seen in the isolated rectangular footing, because whatever the concept that is required towards the design of footing, whatever the type of footing, I have covered almost 80% of the concept in this one. Whatever the leftover 20% that is there, that I'll consider based upon the type of footing that we are designing. Right. So that's from my end for this particular session. If you have any doubts, you can unmute and ask your doubts. Thank you.